Welcome to Recording 1A for Arithmetic Sequences, Unit 1, Chapter 1 of Mathematics 2200. We'll be defining an arithmetic sequence, graphing it, and looking at a formula for the general term. What are arithmetic sequences? They're sequences that have a constant difference between successive terms. For example, if I look at this first one, 9 subtract 4. So I always take a term and subtract the previous one. That's equal to 5. 14 subtract 9 is equal to 5, etc. 19 minus 14 will give me a constant difference of 5 as well. So I should check the rest. 24 minus 19 will give me 5. 29 minus 4 will give me 5. That constant difference is called D, and we will say D is equal to 5. So therefore, this one is arithmetic. In this next one, negative 1 subtract 1. That's equal to negative 2. Negative 3 subtract negative 1. It's like negative 3 plus 1, which is negative 2. Negative 5 subtract negative 3. It's negative 5 plus 3, which is negative 2. And negative 7 subtract negative 5 will give you negative 2 as well. So once again, we have a constant difference of negative 2 rather. So this one is arithmetic. The next one, if we divide a term by its previous term, we get a constant ratio of 3. So we can multiply each term by 3 to get to the next one. But if we check the constant differences, there isn't one. Therefore, we do not have an arithmetic sequence. Now this next one, we're adding 3 blocks on to the figure, or 3 squares on to each figure. So it's 4 minus 1 would be 3, and 7 minus 4 would be 3, etc. So that one's arithmetic. D is equal to 3. Now we're going to graph an example of an arithmetic sequence. We've got a bunch of figures here. They're representing a fence formed from metal rods. So 1 metal rod per side. I've numbered the figures, figure 1, 2, 3, and 4. I'll put them down in my table. They'll be the values of n in this table. Now our first figure is formed by 4 rods. Then the next figure has 3 more joined onto that. So it has 7 rods. Add another block onto that and we get 10 rods altogether there because it's only 3 more rods. Another 3 gets us to 13. Now I'm getting rid of the graph, so I've called my horizontal axis my figure number, my vertical axis the number of rods. Let's have a look at the constant difference here. 7 minus 4 equals 3, 10 minus 7 equals 3, 13 minus 10 equals 3. So our constant difference is 3. Keep note of that. I've got my points plotted. So my figure number is my n values, and my number of rods is my t sub n values. It's a discrete graph because the n values represent the figure number. We can't have figure 1.7, for example. So we do not connect the points. There's a question here about slope. Let's look at that. The slope of the graph. Our rise is 3 and our run is 1 between successive points, so our slope is 3 over 1, which is 3, which equals our constant difference. So we could find an equation for this particular problem just by thinking about y equals mx plus b. The slope would be 3, so it would be 3x, but we'll use 3n. And we could extrapolate back to get our y-intercept at 1. So it would be t sub n equals 3n plus 1. We'll look at another way of coming up with that in a moment. Next, we look at a formula for the arithmetic sequence, or any arithmetic sequence. It is this: t sub n equals the first term plus n minus 1 times d, where n belongs to the natural numbers. Now, where does that come from? Well, an arithmetic sequence starts off with the first term. Then, to get to the second term, term 2, we add a constant difference on. To get to term 3, we have to add yet another constant difference on. And to get the term 4, we add yet another constant difference on. So you'll notice that the coefficient of the d is always 1 less than the term position we're at. That gives us the basis for this formula. We can use that formula to find a specific term, to find and simplify a formula for a sequence to the form t sub n equals an plus b, like y equals mx plus b, and given a sequence, determine the number of terms. Let's have a look at this example. First, we verify the sequence is arithmetic. Well, it certainly looks like we got a constant difference of 1.5, so it is arithmetic. Now let's find a formula for the general term. We start with t sub n equals t sub 1 plus n minus 1 times d. The first term we know is 3, and we have n minus 1. We'll leave that there. And the constant difference is 1.5. To get it into the form t sub n equals an plus b, we distribute. So we wind up with t sub n equals 3 plus 1.5 n minus 1.5. And that simplifies when we get like terms together to 1.5 n plus 1.5 at the end as well. Now we could either use the formula we just found or this formula to find the number of terms in the sequence. This one's actually easier, but lots of times you don't want to spend time finding that formula. So keep in mind we know 181.5 is the last term of the sequence, we just don't know the position it's at. So the nth term, 181.5, equals our first term, which is 3, plus n minus 1. We got to find n, that's good. Constant difference we know to be 1.5. So with a bit of distributing again, we've got this equation. A little more rearranging gives us 180 equals 1.5 n. And dividing both sides by 1.5, we get 120 equals n. So there are 120 terms. Key ideas: arithmetic sequence has constant difference. The graph has a linear pattern, it's discrete. The slope is equal to the constant difference. Has equations similar to y equals mx plus b if you simplify to that form. The domain is the natural numbers. And the formula for the general term can be used to find a specific term, the number of terms in a sequence, or to find a formula and simplify it to this form an plus b.